Okay, we've got a ladder problem here. This is sort of from the moments sort of subsection of forces. If you're doing A level maths, these problems tend to be a little bit tricky, to be honest. I mean, first of all, moments. Yeah, obviously we've got a new concept in there in forces, but if moments problems tend to involve not only taking angular moments, but also using linear um, view of the forces as well. So that kind of makes them a bit tricky. And then these problems, this is a beam, it's basically a ladder problem, um, tend to be another level of difficulty because we have to resolve forces here as well, because obviously the beam is generally speaking at an angle to the ground. So yeah, so they're not the easiest problems, but let's have a look at this one. A beam AB has mass m and length 2a. It rests in equilibrium with A on rough horizontal ground, that's sort of typical, and B against a smooth vertical wall, again, seems to be typical. Inclined at angle theta, and the coefficient of friction is mu. It's modeled as a uniform rod, meaning the mass acts from the center in a vertical plane that's perpendicular to the wall. That just means the beam isn't pointing out towards us or anything like that. Okay, right. So first things first. Uh, as I say with all these things, don't be tempted to start scrawling on your diagram here. Draw your own nice, neat diagram using a ruler and make it neat because you're going to have to understand your own drawing. Um, Two reasons for that, really. First of all, I mean, actually creating this diagram here is part of your problem analysis, so it will help you in that sense. And the other thing is, once you've scrolled on all this diagram, you've spoilt it really. But and if you need to go back to this and look at this, then you messed it up. So I would always say draw your own nice, neat diagram. Right, so we've done that. Got a beam on there, and we're going to add our forces in there. Um, so what have we got? Yeah, we've got the force due to the weight and gravity acting down there and from the middle. So that's mg, mass m. Um, we've got the reaction force here at the base, which is perpendicular to the ground, and then we've got this frictional force here, which is acting. Well, I think we can assume it's acting in this direction. The tendency is going to be for the ladder to slip outwards, isn't it? Um, and then we've got the reaction force at B, which is perpendicular to the wall. Now, I've also drawn in the resolve parts of these two forces here, because then I kind of know I'm going to be taking moments, um, um, are actually about A, in fact, but so I'm going to need those perpendicular to the rotation. Right. So now, so where do we go from here? Well, I think the first thing is we can look at the vertical forces. Yeah, we can look at the horizontal forces. Those are important. But first of all, I'm going to take moments about A. Why A and not B, or anywhere else? Um, yeah, I mean, it's a bit more complicated here. And at least if we take moments about here, we eliminate the consideration of these two forces, and that's a kind of a normal thing with moments problems. And we can at least see a relationship up here. Right, okay. So that's my first step. So when we do that, we get this force acting at a distance of A equals RB sine theta, um, which is acting at a distance of 2a. Right, okay, so what else? Right, well, let's look linearly. And that's often the step. Once we look at the angular moments, and then we'll look at linear forces. What have we got? Well, now the key thing, I've underlined it in yellow here just to kind of highlight it. But what we've got here is, if we look at that, we've only got those two horizontal forces. We're not interested in this case in actually looking at the resolved forces. We're just looking at the actual forces, and that are the only horizontal forces. We have no acceleration in the horizontal sense, and therefore these forces must be equal. So RB is equal to the frictional force. Now, not only that, but when we look at our little equation for friction and normal reaction, um, usually we tend to work in terms of limiting friction, don't we? F equals mu R. But in actual fact, if we're not, that's a specific statement of what is generally happening, which is that the friction must be greater than, unless we've got some acceleration happening, some slipping happening, then the friction is going to be greater or equal to, well, mu RA. It'll be equal at limiting equilibrium, but in general, it's greater than. And the other thing that we note looking from the vertical forces is that the reaction force A is equal to mg. Right, so this is the really crucial step in this in this problem. So yeah, take a moment to just think about that, because you'll see that same idea reflected in similar problems. Anyway, looking at all this together, that's basically, we put these various things together, and it's going to give us that RB is greater than or equal to mu mg. And when we substitute that into our equation here, it turns it into an inequality then, doesn't it? So we basically got mg cos theta times A equals mu mg sine theta times 2a. All right, and if we rearrange that to be explicit in mu, we're going to get this. We've got cancellation going on with mg and a, and cosine theta over sine theta equals cotangent of theta. So it's going to give us the result that we require. So now, yeah, that's sounds easy when you say it like that, doesn't it? But it's but really it's not so easy. But I do stress that is the key part of this. So try and just get to you go over that again. Right, okay, we've got a part B. Right, change the problem slightly in part B. Now a horizontal force of magnitude kmg, where k is a constant, is now applied to the beam at A. Oh, and it's perpendicular to the wall and towards the wall. There we go, in there like that. Given that tan theta equals 5/4, mu equals 1/2, and the beam is now in limiting equilibrium, use the model to find the value of k. Right, okay, so now if we just go back over our key step, it's changed slightly. First of all, now it's in an equality, because we're in limiting equilibrium. And secondly, RB's not just got the friction to fight against, but it's also got this kmg force here coming in here. So RB equals kmg plus F. I usually denote the kind of limiting friction by Fx, bit of notation that I tend to use. We've still got this. This is still the same. Ra is equal to mg. So when we take our moments about A, we got something similar, but our RB is now going to be, well, first of all, it's an equality, but RB is going to be this expression here, F minus KMG. That's just a rearrangement of that, basically. Right, okay. And F is going to be equal to mu RA. Okay. So, in entirety, this is what we've got now. Okay, so similar to before, but we've got KMG in there. It's an equality. So, right, so if we just, again, we got cancellation in MG and A going on. That's going to make it nice and simple. And therefore, if we just bring this term over onto the denominator on the left-hand side, half cot theta equals mu minus K. Cotangent of theta is going to be 4/5, isn't it? Coming from that. Um, um, yeah, so let's write that out in terms of K. Yeah, cotangent is that. The coefficient of friction is a half. So what we've got, that should be a minus sign there. What we've got is, just change that. Minus. Yeah, so we just work that through with a half and our 4/5 in there. We're going to get a half times a fifth, which is equal to a tenth. So use the model to find the value of K. That is what we have done. Right. Okay. So, I mean, in this case, once you've done part A, part B is it's just a slight modification of it. And by the way, I would generally recommend drawing the diagram again rather than kind of messing up your original diagram. If you need to go back and if you've drawn on the original diagram, then you've kind of messed that up. So it could serve you to do it. I mean, if the diagram is very complicated and you've got a very small change, then it may not be worth it. But I would suggest that you consider doing that. Okay. Oh, so that's it. I think it's quite a difficult problem, but hopefully that's helped you and you found it interesting, and you will be able to use that in any other similar problems that you might see. So thanks for watching.